In this question, we're going to talk about the applications of the dot product and the cross product. Suppose F, as shown, the diagonal force going up to the right, is a constant force operating on an object at the point O, so that the object moves from O to A. And let S, with the arrow on top, the vector, be the vector from O to A, and let S without the vector on top equal the magnitude of OA, and that'll be the scalar representing the distance the object's displaced. Well, we know from physics that work is a scalar quantity equal to the magnitude of the force applied to the object in the direction of movement times the distance moved. Now, the distance moved is just equal to the magnitude of the displacement, which is the magnitude of the vector S. And we know from trigonometry that the magnitude of the force applied in the direction of the displacement will be the magnitude of the force times cos theta. It's like the horizontal component in a sense. Since work is equal to force in the direction of movement times distance traveled, we can say work is the magnitude of the force F times cos theta times the magnitude of the displacement. In other words, magnitude of the force times magnitude of the displacement times the cosine of the angle in between them, which is another way of saying F dot S. So work is equal to F dot S, where F is the force vector and S is the displacement vector. Now, when force is measured in newtons and displacement is measured in meters, then work is a scalar quantity measured in joules, and we can say 1 Newton meter is equal to 1 joule. So we'll do an example here involving work. Suppose Mariana is pulling her daughter in a toboggan and is exerting a force of 40 newtons acting at 24 degrees to the ground. If Mariana pulls the child a distance of 100 meters, we'd like to know how much work was done. So we can draw our vectors as such. We've got a 40 Newton vector and a 100 meter displacement vector with an angle of 24 degrees because we assume the child was, pulled along the ground, obviously, and we see that the 40 Newton force is acting at 24 degrees to the ground. So the work will equal F dot S, which will be 40 newtons times 100 meters times the cosine of 24 degrees, which is roughly going to equal 3,654 Newton meters, or in other words, 3,654 joules. Now, in a previous video, we went through and established some formulas that are going to help us next. But one of the formulas that's going to help us is to know that the area of a parallelogram determined by the vectors A and B is equal to the magnitude of the vector A cross B. And since a triangle is 1/2 of a parallelogram, therefore the area of a triangle determined by the vectors A and B will equal 1/2 times the magnitude of A cross B. So suppose in 3 dimensions we had a parallelogram determined by the vectors 4, -7, 5, and -1, 0, 2. If we wanted to know the area of the parallel, so what you can do is kind of imagine vector A and vector B, and then a parallelogram would kind of look like this. I didn't do a great job drawing them as parallel. And what we're looking for here is the area of that parallelogram. Well, the process is actually quite simple. All we do is determine the cross product of A and B. The cross product of A and B will be -14, -13, -7. And then we simply determine the magnitude of that. So it's the square root of -14 quantity squared plus -13 quantity squared plus -7 quantity squared. In other words, it's the square root of 414 or 3 root 46. So the area of the parallelogram described in this question is 3 root 46 square units. So another question might ask us the area of a triangle. Again, just do the cross product. As we've seen how to do, we see that the cross product is -7, -54, -3. We want to determine the magnitude of that vector. The magnitude of that vector is root 2,974. But since we're determining the area of the triangle and not the area of the parallelogram, our area will be 1/2 of that. The reason being, if I have vector A and vector B, If I'm looking for the parallelogram, that'll be this whole area here. But if this is vector A and this is vector B, and I only want the area of the triangle, that's going to be 1/2 of that parallelogram. So that's why we put a 1/2 in front there. Okay. Now, finally, we'll talk about torque. Torque is the turning effect of a force about a point. And in the diagram shown, the torque of the force F about the point M is defined to be the vector r cross F. And the magnitude of the torque is the product of the magnitude of the force and the distance d. Now, the force is measured in newtons and the distance d is measured in meters. So the unit of magnitude for torque will be newton meters, or in other words, joules, which is the same amount that work is measured in. So imagine that we have a 20 Newton force applied at the end of a wrench that is 40 centimeters in length. The force is applied at an angle of 60 degrees to the wrench. We want to calculate the magnitude of the torque about the point of rotation, M. So since we're just looking for the magnitude of the torque, what we're looking for, since torque is r cross F, the magnitude of the torque will just be the magnitude of r cross F. In one of our previous videos where we established formulas, we said that the magnitude of A cross B will be equal to the magnitude of A times the magnitude of B times the sine of the angle in between them. So since torque is equal to R cross F, therefore the magnitude of torque is equal to the magnitude of R cross F. Using this principle right here, we can say that's equal to the magnitude of R times the magnitude of F times the sine of the angle in between them. Well, the magnitude of R is 40 centimeters, the magnitude of F is 20 newtons, and the sine of the angle in between them is sine 60 degrees. Now, we can write that here. Remember, though, that joules are measured in Newton meters, so we're going to convert our 40 centimeters to meters. So we get 0.4 meters times 20 newtons times approximately 0.8660. That's roughly equal to 6.9 Newton meters, which is 6.9 joules. And so we can say the magnitude of the torque will be roughly 6.9 joules.